Hello, and welcome to our presentation on approximate fault tolerance in distributed optimization. I am Nirupam. I am a postdoctoral fellow in the Distributed Computing Lab at EPFL University in Switzerland. And in this video, I will present my joint work with Sho, who is a PhD student in the CS Department of Computers of Georgetown University, and along with Professor Nitin Vaidya, who chairs the CS Department at Georgetown University. In this short presentation, we will present our recent results toward unification of this problem of Byzantine resilience in distributed optimization. Our paper, as shown here, was submitted to this year's PODC 2021 conference. And the talk is broadly divided into two parts. In part one, we will present our results on the feasibility and achievability of fault tolerance in the context of distributed optimization, and we'll show how our results generalize the prior feasibility results and consider the special in context of heterogeneous distributed learning and distributed sensing problem. In part two, we show how to realize this goal of approximate fault tolerance, or characterize this goal of approximate fault tolerance for distributed gradient descent algorithm, which is widely used for distributed learning and distributed state estimation applications. And we'll present some techniques that are widely used for this particular problem setting and how to characterize their fault tolerance properties. Okay. So before we present our results, let me introduce this particular problem of fault tolerance in distributed optimization. So the system comprises of multiple agents. Each agent I has a cost function QI with a multivariate cost function, and the objective in all the agents that are fault free is to compute a point that minimizes the aggregate of all these cost functions. We consider a scenario where some of the agents are Byzantine faulty, that is, they can arbitrarily deviate from the prescribed algorithm and disrupt the optimization process. Consider up to F out of N agents to be Byzantine faulty. In presence of such faulty agents, obviously the original goal of minimizing the aggregate of all the costs is rendered vacuous. A new, more reasonable goal, as formally stated by F resilience here, is to compute a point that minimizes the aggregate of at least n minus f or n minus f honest cost functions. This particular goal of F resilience is colloquially also known as exact fault tolerance and was implicitly originally proposed by Lilly and Nitin in their 2016 PODC paper. When F equals 0, this is just the original optimization goal. Okay, so recently in our work in last year PODC paper, I guess, I and Nitin, we showed that exact fault tolerance is achievable if and only if the agent's cost function satisfies the property of 2f redundancy. This particular property of 2f redundancy, which is formally defined here, means that the minimizer of the aggregate of any n minus 2f costs is also the minimizer of the aggregate of all the honest costs, and vice versa. In theory, you can realize 2f redundancy by design. However, in practice, it is difficult to realize it due to unmodeled noise, unknown uncertainties, hardware failures, etc., etc. Moreover, this particular notion of exact fault tolerance and its relationship with 2f redundancy is inadequate to characterize the relationship between redundancy and resilience in the system. That is, how worse or good can resilience get with weaker and stronger redundancy properties. Towards this goal to overcome these limitations and to derive this characterization of relationship between redundancy and resilience, we generalize or relax the exact fault tolerance goal and propose the objective of approximate fault tolerance, formally epsilon resilience, where the goal is to minimize the aggregate of honest cost with epsilon accuracy. We also relax the 2f redundancy property, where we say that, okay, the minimizer of aggregate of any n minus f cost function is epsilon close to the minimizer of the aggregate of all the honest cost functions instead of being the exact same. Now, when epsilon equals 0, both these notions reduces to the original notion of F resilience to F redundancy. There are other notions of fault tolerance than ours. For example, this notion where you can output a minimizer of the weighted aggregate of these costs that aggregates the weights need not be uniform, so it's not it's slightly different than exact fault tolerance. And it was also proposed by Lilly and Nitin in the 2016 paper. However, the characterization of this approximation is only well understood for the scalar cost and poorly understood for the high dimensional case. Another notion is to limit the magnitude of the average gradients by epsilon as shown here of the honest cost. And this notion was proposed in the machine learning community, specifically by Dia Nicolas and colleagues in 2019. And it's sensitive to scaling and assumes differentiability, unlike F epsilon resilience. Moreover, epsilon resilience reduces to this particular notion of approximation under regularization, such as Lewis smoothness. So epsilon here quantifies the loss of redundancy. Larger is the value of epsilon, we get weaker redundancy, and vice versa. It can be satisfied for any system with different values of epsilon. And it enables us to derive the limitations of Byzantine resilience that are feasible in the system. In context of distributed learning, it helps us characterize resilience against heterogeneity in context of distributed sensing, the impact of noise on resilience, as we'll see shortly these two examples. So we show that you cannot achieve F epsilon resilience unless you have 2F epsilon redundancy. So if the system doesn't have any more redundancy than 2F epsilon, you cannot obtain the honest minimizer with more than epsilon accuracy or better than epsilon accuracy. Moreover, when you have 2F epsilon redundancy, then by construction, we have shown that you can indeed achieve two epsilon resilience, where you can approximate the minimizer of honest cost with 2 epsilon accuracy. So there's a donut in which the solution of any algorithm would lie, and you cannot guarantee a solution which is closer to the true solution than epsilon. And you're guaranteed to, if you design a clever technique to obtain this honest, to approximate the honest minimizer by 2 epsilon accuracy. Let's see how this applies to the distributed analysis problem or learning with outliers. So you have these clusters of agents. Each cluster has different solutions, xi. Now, when these data sets are kind of heterogeneous, they're different from each other. And the more is the heterogeneity in the system, the worse is the resilience. And epsilon can be thought of as a measurement of diversity. However, this is a bit at odds with the general trend these days, where you try to have more diverse data for better generalizability. But better generalizability, as we are saying, is not doesn't go in hand with better with resilience against Byzantine participants. As you can see, you must have different images for a single object to have a better generalized model learning procedure. However, this gives you a larger area of vulnerability and poor resilience against data policing attacks. Similarly, in distributed sensing, we have multiple GPS satellites trying to locate you, but each satellite's measurement has corrupted by noise, and this corruption of noise is impacting your Byzantine resilience of the system. That is against a GPS spoofer, where if one of the GPS gets sending you corrupted information, you get better resilience with smaller noise and better security against GPS spoofing. Okay, so this brings us to the end of part 1. And for part 2, I would like to invite Sho to discuss more on the realizability of approximate fault tolerance and distributed gradient descent algorithm.
Thanks for Nirupam's presentation. Now let's dive into achieving Byzantine resilience in practice using distributed gradient descent, or DGD, which is an iterative optimization algorithm. Let's see this system architecture here, where there's one server communicating with multiple agents. The server selects an initial estimate x as 0, and for each iteration t, first the server broadcasts xt, the current estimate, to all the agents. Then each agent I computes the gradient gi of its local cost function qi, add the current estimate xt, and send it back to the server. The second step is that the server aggregates the gradient it receives to update the current estimate. Basically, it sum all the gradient up or average the gradient, and then times it with eta t, which is the step size. Now, if there are Byzantine faulty agents in the system, shown here, the red node in the figure, we will need something called Byzantine robust gradient filters, or gradient aggregation rules. A gradient filter robustly aggregates the gradients instead of simply averaging them. It is actually a function that takes n vector of the same size, including good gradients from non-faulty agents and arbitrary vectors from Byzantine faulty agents, and return a vector of the same size that can be used by the server to update the model. There are multiple gradient filters proposed, including Chrome, geometric median means, Boolean, coordinate-wise tree mean, and the comparative gradient elimination. Here we show two examples. First is comparative gradient elimination, or CGE, proposed by Nitin and Nirupam in 2019. It removes gradients with f largest norms. Here, 6 vectors, 2 of them in red are from faulty agents. The filter will remove 2 vectors with the largest norms. The intuition here is that either faulty agents are removed, or if a vector from faulty agents are kept is kept, there is always a good vector out there with a larger norm bounding it, so that even if we're going to the wrong direction, we're not going too much. Second one is coordinate tree mean, proposed by Lily and other authors. So for each coordinate, it removes f largest and f smallest values, and then it computes the mean. Example here shows, suppose there are 6 values for a certain coordinate. The trim step will remove 2 smallest values and 2 largest values. And the mean step, we compute the mean of the rest of values and get 2.5. And we repeat this process to all the coordinates in the parameter estimation. Now, what kind of resilience can we achieve? So the general result is that with 2f epsilon redundancy, DGD with any kind of gradient filter can achieve f big O epsilon resilience, where the approximate parameter big O epsilon is decided by what gradient filter you're using. Specifically, we study 2 gradient filters, CGE and coordinate tree mean, and we show that CGE requires f smaller than n over 3, and the resilience of coordinate tree mean is independent from f, but it relies on additional assumptions over the cost functions. And also, CGE is independent of the size of the parameters, while coordinate tree mean dependent on that. Now we show some experiments. We did some machine learning experiments using distributed stochastic gradient descent instead of plain DGD. The applicability of our results over stochastic gradient descent is discussed in our paper and also by Nirupam previously. So here we simulate a system of 10 agents. 3 of them are faulty. The data are uniformly distributed among the agents so that no 2 agents obtains the same data point. We simulate 2 types of faults, label flipping, where we scramble the class labels of the data points obtained by faulty agents, and reversing gradient faults, where faulty agents will reverse the direction of the gradients and then send that vector to the server. So first we show the experiments using MNIST, which is an image classification task, training a model of LaNet, which is a neural network. They're both benchmarks. The result here, we see that no matter what gradient filter we're using, no matter what kind of faults we're facing, algorithm converges to comparable accuracies to the case where there's no faulty agents in the system. So it shows that our algorithm works and the resilience actually exists in a real-world scenario. The second experiment is that we conducted on Fashion MNIST, which is another image classification dataset with the other settings kept the same. And we see that the differences between gradient filters and the types of faults they're facing are more significant than the previous one because this task is more difficult. But still, in all cases, they're converging, and they're converging to a close range to the case where there's no faulty agents in the system, which complies with our theoretical analysis. There is another group of experiments from our previous paper accepted by DSN, DSML workshop, where instead of distributing the data to agents, each agent have the same data set, which means that all agents have the same cost function in expectation. In that case, we tested multiple gradient filters, and we see that they're all converging and the differences are smaller comparing to the case where data are distributed. And also the running time shows that some gradient filter like CGE and the Cordon-Weiss tree mean are actually faster than some other gradient filters like Crum and geometric median and others. So that there's a kind of a trade-off between the running time and the accuracy you can get among the gradient filters. To see the details of our present work, including our paper and the previous paper of DSN, the full version of them can be found on arXiv. And you can also see the papers discussing resilience of optimization and redundancy among cost functions. Our research is supported by NSF, ARL, and Georgetown University. And these are our emails. Thank you. And if you have any questions.